Maybe you have very good eyes, or you'd better be closer. So this program is on the circle method and large sieve. I'm somehow responsible for the more classical introduction of the large sieve. That's going to be my topic. Can you read this, or should I write bigger? A bit bigger? I can see people, okay, a bit bigger. Okay, what are the players? I will have a sequence UM always, and this is a finite sequence, or say UN, n less than n. And typically it's going to be the sequence of primes between 1 and n, or it's going to be the sequence of squares. I mean, it's a sequence I want to study. And my main concern is going to look at this function S of alpha is this one, so for n less than n, of un E n alpha, where E beta is exponential to I pi beta. So you'll see in the way sound presented the circle method, you didn't see this linear form in the UN, but they'll occur during the week constantly. So we have this function. What I would like you to know first, what is of main importance is the length. The length is n. Sometime I will have the sum for m, n, n plus m, p, sorry, of E of p alpha, which means that I look at the primes between m and m plus n, and I'll still use the same thing because it's just a shift and it's not going to change anything. So don't, sometimes I'm going to get confused between this form and that form. It goes easily from one to the next. Something I want you to notice is that, look here. Up. When alpha equal a by q, and you can guess that when I write a by q, a is an integer and q is an integer. S of a by q depends only on un modulo q. That's what I'm going to say. What does it mean? Depends on un modulo q. Un is a complex number. It's a modulo q. It doesn't exist. What does it mean is that if you look at this variable fqb, which is a sum for n congruent to b modulo q of un, these are the variable of un modulo q. And when you look at SA by q, only this variable intervene. Some people are not convinced. It's a course. You can stop me whenever you want, you know. Okay, so if you're not convinced, I'm going to prove it. I hope I'll be able to do that. Let me do it here. No, not a good idea. SA by q is a sum for n less than n of un n a by q, which is a sum. I can split my summation. Okay, so this one was my definition. This one is a partition. If I look at the integer, I can split according to arithmetic progression modulo q. And now that I have n congruent to b modulo q, yeah, it's coming. It's coming. I have n a by q, But this one depends only on n modulo q, so I can put a b here. It's an animated talk. Sound has this nice way of putting a round, and the round was disappearing. My B will stay. And now you have this one, okay? I can still continue. I have so many blackboards. Okay, so what is the large sieve all about? Principle of large sieve. One, prove a local lower bound. I'm going to give you an example just after that. Essentially, I'm going to prove some lower bound that implies these variables. To prove a global upper bound. This global upper bound is usually, it can be the large sieve inequality, but I'll show you in the third lecture that you can use the Parseval identity in the same manner. Combine the two, get the result. So I'm going to show you how it works for the primes. For the primes. I am going to prove that the sum for, so you can still read here, okay? Mod, I'm going to tell you what it is, of S A by Q square is larger than, wait. Just I have to be more precise, sorry. I forgot something here. When I use this one, I use capital M to be larger than square root n. To simplify my life, I assume that. The advantage is that all these primes here are co-prime with any integer q which is less than square root n. That's why I do this little stuff. It's so for the primes, take q less than square root n, strictly less than square root n. We will prove that the sum for A mod star q of SA by q, I'll do that in the second part of this lecture, today. Larger than mu square q upon phi of q S of 0 square. So this one is 1A q and A prime to q. I put mod star. When I say mod q, it's a complete system of residue. When I put mod star, it's that they are invertible. They are coprime with q. So you have phi of q guys here. This trigonometric polynomial is the point A by q. When you do this average, I'm going to prove that it's larger than this one. So this one is S of 0 is the number of elements. You divide by the Euler-Phi function, and it is valid only when q is square free. When q is not square free, I don't know what to do. It's a difficulty. So that's a local lower bound. Local because it depends on in modulo q, and it's a lower bound because it's a lower bound. Okay. And this one I can still, okay. We will prove tomorrow that the sum for q less than capital Q and the sum for A mod star q of S A by q square less than n plus q square the sum of MP m plus n of 1 square, in fact. 1 square, to tell you that it's going to be the L2 norm. But the L2 norm of something which is 0 or 1, it's 0 or 1. Yeah? So this one is S of 0. So I'm going to prove this one for any parameter Q. Now you have a lower bound for this guy, which is given here. So assume that capital Q is less than square root n, so that this lower bound applies. So this one is larger than mu square Q upon phi of Q times S of naught square. And what you get is that the sum for Q less than capital Q of mu square Q upon phi of Q, S of naught square less than n plus Q square S of naught. That's what I'm going to expand in more details with more complicated functions, but that's Montgomery sieve, that's the last sieve. What you get, you simplify by S of naught. No, you don't simplify by S of naught. If S of naught is 0, you're happy. If F of naught is non-zero, you simplify. And you get that S of naught is less than n plus Q squared divided by something. So this something, this time I have to go back. Maybe you've proved in as exercises, or we'll do it at some point of time. It's a very nice exercise. The sum for Q less than Q of mu square Q on phi of Q. Phi of Q is of size about Q. You know, phi of Q is a product of Q of P minus 1 for P divides Q. So it's about the same as the product of P for P divides Q. So it's about Q. So phi of Q is about Q, and this one should be about log. Now, in fact, you can show that it is larger than log Q. Very simply. I'll do that at some point of time. So what you get, consequence, the sum of the primes between m and m plus n of 1 is less than n plus Q squared upon log Q. For any Q less than square root of n, I have this bound. So we're bounding above the number of primes in an interval. And that's going to be a main theme in Sieve and in the kind of Sieve that I'm going to handle. We're going to get upper bound of sequences that have a local property. This one is that you have this inequality here. So that's my local property that depends only on modulo Q. You look only as integer modulo Q, what happens? And we will get only an upper bound. If you get a lower bound, you come to see me and we can talk. So what is your choice of Q here? Who can propose me a choice? No, Jean-Marc, yes, but no. No. Okay, take a Q equals square root of n. Okay, you want to take Q large. You want to take Q large, but this one to be negligible, because you don't want to spoil this one. So you take root n, but you save just a bit. Say divided by log n. because then log Q is going to be 1/2 of log N plus little o. And this one is little o of that one. And what we have proved, I'm going to save a bit of ink, and I'm going to state a more general theorem. And huh? What? Oh yes, yeah, sure. Theorem, and you're going to hear this name again and again, Braun-Titchmarsh theorem. Let Q be larger than 1, that's a modulus. Let K larger than 1, sorry. Because otherwise I'll get confused. Let N be larger than K. We have the number of primes P in an interval M plus N and M of 1. It turns out that I've done it only for all the primes, but you can add a congruence condition for P congruent to some B modulo K is less than 2, 1 plus little o of 1, N upon phi of K log N by K. Okay? So just forget about the K for the time being. What I've proved, I've given you a proof somehow that the number of primes in an interval is less than 2n upon log n. You can accommodate, the same proof will work in an arithmetic progression, and you get 2 upon phi of k log n upon phi of k. So what do you believe? You believe that the number of primes, I mean, you know that the number of primes between 1 and n is n upon log n. So you seem to have lost a factor 2. What you have gained is that it is valid in any interval. Now, if you have an arithmetic progression modulo k, the primes are only in invertible classes modulo k. You have only phi of k of them. You believe that the primes are well distributed in them, and it's true if k is small. So the good main term should be n upon phi of k divided by log n. And you've lost a factor 2. Okay. Essentially, this was proved by Selberg in 47, something like that. And Selberg did not notice the factor 2. I mean, you know, people have some proof, but you try to get the best of that you can, and you compute your constant, you get a factor 2, you say it's a factor 2. It is called the Braun-Titchmarsh theorem. Oh, it's an I here. Not because Braun proved it, not because Titchmarsh proved it, in fact. Because Linik in 1961 wrote a book, The Dispersion Method in Analytic Number Theory. And he puts a lemma, which he says you can get it from the paper by Titchmarsh on the divisor problem, the number of divisor of P minus 1. And it is proved by the method of Braun. And if I remember well, there was a log more here, but so since then, we call a Braun-Titchmarsh theorem something that looks like that. In fact, nowadays, we have that. Okay? We're able to prove this one with no error term. That's due to Montgomery and Vaughan. But I'm still going to say Braun-Titchmarsh theorem for any version of that. Whether there's a 2 plus little of 1, whether there's not 2 plus little of 1, it's not a fixed name, it's a generic brand. You know? But now let me have a look at, let me talk about this factor 2. K is bounded by n, K can be extremely large. But it's an interesting remark because of two things. I told you the number of primes is n upon log n. That's false. Just imagine capital M is exponential n. So this interval is very small part next to a big part. Then the density of primes is log m, not log n. And here we have log n and not log m. So there's a definite loss here. And also, if k is n to the 1/2, then you lose a factor 4. You don't lose a factor 2. Okay. There's a big fight when k is a power of n. Essentially, for what I'm going to do, it's enough to consider k less than log cube. If you want to kill Ziegel 0, power of log is enough, so you can assume that you don't have that. But it's true that it's n by k and not n. As there's been a paper by many people that puts a log n. I think Maynard can put log n till k is n to the 1/4 or something like that. I mean, there's a fight on that. Cool. So then, what about this factor 2? What about this factor 2? Huh? Yes. It's really uniform. It's in fact because my linear variable s of a by q, if one shifts by m, you only multiply by exponential m alpha. With the absolute value, it disappears. So it's fully uniform in m, which is maybe a weakness. We are not able to use the relation between m and n. I mean, it's a strength because the result is very general, but the proof is not able to detect the link between m and n. Maybe it would be better if we were able to detect it. Okay. Theorem should be in the 70. I have to be a bit precise because otherwise you run into difficulties. So this one is 1973, and this one should be let's say about 1979. But several results were proved that somehow the community got the idea that it was true. I'm going to tell you that if you beat these two here, you show that there's no Ziegel 0. So you solve the class number problem, you get the field medal in between, and essentially you'll be happy. And then I won't have any job anymore and I'll go to the mountain to hike. Okay. There exist two. It's important to put effective. Effective means that I could compute them if I were not lazy, but I'm not going to compute them. C1 and C2. Sorry, it's going to be C2 and C4. I don't remember why, but that's that. Oh, okay. Oh, sorry. Just before you do that, these lectures are going to be at two different levels. The one that I present here is a basic level, if you just want to know about the large heap. If you want to know more, there's a notes that are on a web page. This web page, it's still secret, so you cannot get it by Google. So you have to look at ramare.olivier.github.io. Okay? Yes, sorry. Here. This one is just a GitHub website. dot input output slash course, but in French, so you forget the E. ICTS 2026. That's my web page and on that you'll find the notes. Okay, the notes are much more complete than what I'm going to present. So if you want to study the material, you can read the notes, you can ask me questions, and you can correct the notes. You have to see that there are notes. And just now I saw a mistake in the variables. So this is the version 5 just now. Let's hope that the version 7 will be more stable. Okay, back to this one. Such that for K larger than C4, the following conditions are equivalent. One, there exists, it's better to write everything fully. Psi, put any letter you want. Psi, that's a psi. That's supposed to be a Greek psi. The students and myself, I write it in a special way. Greek people will not recognize psi, but LaTeX it's a psi. A positive psi, such that for any B prime to K, we have the sum of the primes less than n, primes congruent to B, modulo K of 1 is less than 2 minus psi upon phi of K log n times n. Okay? So meaning that you beat Brundtland-March without the by K, because in fact K is less than some power of log. 2 minus psi, you beat the factor 2 by something. So you prove 1.99 and 2 wait. Oh, sorry. I forgot my C2. We have for n equal Q K to the C2. Yes, because I wrote the other one. Okay, no big deal. So this one is for a power of K. Okay, I'll tell you what happened when it's not. So if you prove for this very special value, so some power of K, which may be as large as you want, yeah? You beat this one. Then you have for any real character, quadratic character, sorry. Anyway, you have for any n or real for any character anyway. Modulo K, L 1 chi larger than 1 upon log K. Okay? So let me be more precise because I said two things at the same time. So if you able to beat that at for such a small n, you prove that it's larger than 1 upon log K. If you can do that for n larger than exponential K, you still beat the 0, but you get 1 upon log, log upon log, something like that. So essentially, you can assume that k is less than, if you want to beat Ziegel 0, you can assume that k is then less than log n to the cube. At the beginning of the difficulty. Log n square, you know how to do. The beginning of the difficulty is log n cube. But the fact is that if you beat fully, without the n by k here, then you get full lower bound for L1 chi. And more clever, I mean, more knowledgeable people here will explain to you why proving that will prove lots of things in algebraic number theory. You get the class number of quadratic field is very large and so on. Okay, so then when people saw this one, there was quite an interest in the Brundtland-March inequality. But you see, this one is 79, 73, 79. And in between, nothing much has happened, in fact. I mean, from this aspect, nothing much has happened. So what I'm going to do, what I'm going to do in these lectures, tomorrow I'm going to prove you somewhere, I lost it, the large sieve inequality in one classical manner. The day after, so on Wednesday, I'm going to reprove this inequality, or at least the Brundtland-March inequality, by using the circle method, or by using the Parseval inequality that we use in the circle method, so that you'll see both approaches. Tomorrow I'm going to prove that this one implies that one, okay? Because that's the one I'm interested in, okay? You can prove that this one implies that one, but I don't believe, I mean, that's not the aim of the game. The aim of the game here is to try to develop sieve method so that we can prove this one. And yeah, now I have to tell you about more, to talk to you a bit more about sieve. Yes. I have to talk to you about examples. Yeah, and in the final lectures, somehow you can guess from what I showed you that what is important are the large values of SA by Q. Because we proved the lower bound for SA by Q, and it got linked with our global upper bound, it gave us a bound. So we want to detect where SA by Q, S, the trigonometric polynomial, where it is large. Is it really in the point A by Q, or is it in other points? What can we say about that? And that will be my fourth lecture. I'll show you that in general, at least for the similar to prime case, the points are indeed in A by Q. And I'll show you also, I mean, you'll see that the proof I'll give on Wednesday somehow look optimal. You have the feeling that you don't lose anything according to usual conjecture. So you continue and you see I'm going to beat the factor 2. And at the end, you have a factor 2. This factor 2 here, up to now, it has been proved in 2 different ways. So by Selberg sieve, that's what you get. But the large sieve, that's what you get. By the combinatorial sieve, in fact, that's what you get also. We have no, if you can say, tell me, assume I assume a Langlands conjecture of anything which is not exactly that, okay? And from this conjecture, you can beat the factor 2, that will be valuable. Assume the generalized Riemann hypothesis, assume whatever you want, but not that or that. No, not the generalized Riemann hypothesis, because you get this one. Except for the line from the 0 on the 1 line. Okay, I told you about primes in, yeah. So some examples. So my main example are primes in an interval. That's really, I'm going to concentrate on this case. I'm even going to forget about the congruence condition K, because usually if you can prove it, if you can do something without K, with the kind of method I use, I can do it with K. So it is simpler to do it without, and then we see what we can do. So that's a major example. Another example is a twin primes. So I guess you know what it is, could be. So it's primes P, that's that P plus 2 is prime. So if I have to give examples of application, I'll use this example or I'll use that example. These are the two simplest one. There's no variable. But in fact, if you want to work, there's two other examples that I like quite a bit. I'll start with the second one. Take n. Assume it's a primitive Gaussian integer. Any idea what can that be? Gaussian integer is a square plus b square, okay? Primitive is that a and b should be coprime. It's too simplified. It's simpler to do them like that. I'm going to assume that they are odd, because also the prime 2 behaves badly, so I assume that they are odd. Such that n plus 2 is, n plus 4, sorry, is also a primitive Gaussian integer. That's really my main example these days. This one is a sieve of dimension 2. I mean, we remove two classes modulo H prime P. We have no idea how to handle it aside from the sieve. We're dead. Primitive Gaussian integers. It's integers that don't have any prime factor congruent to 1 modulo 4, no, the reverse, congruent to 3 modulo 4. They have also some nice property that it's enough to remove the primes that are below the square root of them. And so it's a sieve of dimension 1/2. The sieve is able to give you an asymptotic for this one. When you add the condition that n plus 4 is also an odd primitive Gaussian integer, you have a sieve of dimension 1. So you know an upper bound, and by sieve reversal, you can get a lower bound of the good order of magnitude. So for this one, you don't have no lower bound. Okay. For this one, you know that you have enough integers. You know that this sequence is very large. And in fact, I thought that if I'm going to tell you that it's very large, I should give you the first examples. So it's 1, 13, 25, 37, 61, and so on. And in fact, it's the example of the prime twin. You know, you remove two classes, but modulo only half of the primes. You have lots of you may use some geometry, because you have Gaussian integers, you have a representation and a square plus b square, you may do other things. So really my difficulty is to understand these guys more precisely. Can we get bilinear form representation? What we know how to do with the primes. And the third example that we've been studying with Cassie Visvanadham from Berhampur. But this one, somehow we understand what is happening. A fourth example, which is true to It has been introduced by Fourier, Levesque, and Waldschmidt. So I was studying some binary form. So take n, say it's an odd, always because it's easier, a primitive integer, primitive Gaussian. Integer. And just assume that it's also an odd primitive integer. And Gauss is being replaced by someone less known, which is Loesch. So Loeschin. So this one is u square plus v square. And this one is u square plus uv plus v square. So this one are the integers that don't have any prime factor congruent to 3 modulo 4. This one is the integers that don't have any prime factor congruent to 2 modulo 3. Okay. They behave in the very similar way as to the Gaussian integer. When you put the two conditions together, you get a sieve of dimension 3/4. And you don't get any geometry anymore because it's the geometry of this one that is the geometry of that one, which behaves badly. But still, with Cassie, we've been able to do many things on this set. But what we do has no bearing at all here. As soon as you remove two classes or more than two classes, we are dead. Then we are going to stop now, and we come back. Yes. Well, in 5 minutes, I'll present a general sieving problem, and I'll prove the lower bound I showed you and some other things. In between, you can show that there's the factor 2 can be beaten easily. For what? Reference. Maybe maybe it's written in the paper I have with Cassie with Van Adam. No, have a look at it, but so this one is with Cassie, GK, Isva, Na, Lam, am I? Our last paper. And we show what we can do, many things we can do here. But I don't know whether we say that we cannot do, you know, sometimes in papers, you don't write what you don't know how to do. You know what you know how to do, but not what you fail in doing. It's, huh? No, it's just to avoid local abstraction. That you would not tell me by some stupid stuff. You know, for instance, if you want to take something that is a prime, that p plus 2 is a prime and p plus 4 is a prime. Huh? If you look modulo 3, p plus 2, p plus 4, they cover z by 3z, so one of them is divisible by 3. Okay? So you have to avoid this local abstraction. And I'm not sure what happens with plus 2. I know that my favorite example is always plus 4. So. But it's just to avoid local abstraction. Oh, yes, sure. Yeah, you have the proper lower bound if you replace 4 by any. I mean, this one we know that there's more than constant x upon log x. I don't even think we know the asymptotic. But really, we have no precision. I mean, though it should be simple. If you look at it, if you look at what we know how to do, it's somehow the level of difficulty of the primes. If you have dimension 1, it should be the level of difficulty of the prime. We're also interested in studying this one so that we can understand better what are the special properties of the primes we're using. Once we understand what are the special property, we can push on this property to get better things on the primes. Because otherwise, it's so general that you don't see exactly what are the special things that you're using. So let me get ready. No. No, because, yes. Yeah, it's already good if people understand that. But you know, the fact that you have two concurrent classes.
Easier.
Yes. Yes. So we saw with classes that what happens here is that you remove only one class, not many auto primes, but only one class. So you can parameterize. No? So that's why we can do some bilinear form and we can get S, you know, so the kind of Vinogradov bound we can get. Okay, we miss a power, but we can do that. For this other one, you know, you remove two classes, no idea. So we have sieve reversal, but aside from that, nothing. I like this example. I like this example because finally we get an example which is not of dimension 1/2 and 1. So,
yeah, 3/4 is
yes,
something peculiar.
Yeah.
In part,
Okay. So to resume, let me start with a one-line proof, and then I'll do something more complicated. Let me call it a lemma. Let me state it like that. We'll see whether you get the statement. When UN is supported on prime to Q element, integers. Oh no, it's not a good one. It's another one. On prime to Q integers. And Q is a square free. Just dot. We have, I'm going to give you a bit more. We have this one. I'm going to add this one to be sure that you don't forget it. Don't get mistaken, it's L1. Okay? In fact, I'll use only L2, but I want to tell you that we have L1, which is stronger, because from this one you can deduce the L2. Huh? Yeah, I've added a mu square, which is the same as a square free, but it's so that you don't forget that it is a square free, so I put it twice. To be sure, I put a belt and some, I don't know how you, suspenders. And this one is very specific to the primes. I'll show you some more general sieving situation. I don't know how to mimic this one. So the proof, you write what? Oh, S of, you write sum for A modulo star Q of E n A by Q equal, if n is prime to Q, what is the value? Huh? Yes, mu of U. I had to talk about Ramanujan sum in India. Anywhere with primes, you always have Ramanujan sum. So you'll see that in my note. Sometimes I defend them, but I use them so often. So. And sum for n less than n of un times the sum for a mod star q of e n a by q equal up mu of q times the sum for n less than n of un. Yeah. And since I've assumed that un is 0 if n is not prime to q, this works. And so put exchange summation, put absolute value, you're home. I mean, it's difficult to find a shorter proof than that. Okay, I've used the lemma, which is equal to mu of q. That you can do by multiplicativity. Okay, I have to show you that it is stronger than what I need. Just apply, if you want to look at S naught square, then it is less than the sum for A mod star Q of S A by Q square, which is less than 5Q, the sum of S A by Q square. I just write that because some people are not used to using Cauchy's inequality. And in analytic number theory, we use Cauchy's inequality over and over again. So I just state it. So you see, this one is larger than S of naught divided by phi of Q. I would like you to notice something else. I'm going to use that not for the integers between 1 and n, but in an interval. Like I told you, sometimes in an interval, sometimes it's between 1 and n, it's the same. Also, this one, we believe it's an equality. Not exactly asymptotic equality. Because we believe that SA by Q is S of naught divided by phi of Q. So if you have S of naught divided by phi of Q times, you have S of naught. That's going to be important. So we believe that we don't lose anything when we employ this part. Because as you can see, I'm going to try to see where the factor 2 is coming from. So I'm trying to locate, and here I don't have the feeling that I'm losing anything. So I'm going to state SA by Q. Yes? Yes. Yes, yeah. It doesn't affect. Yes. You just lose the sign. Because it doesn't affect because they are all equal. So in fact, it's like you multiply by a number. So the number, you can put it in front or inside. Yeah. So we believe that S A by Q is equivalent to S of 0, mu of Q, S of 0 upon phi of U. And it is true, for instance, for the primes between 1 and n, if Q is not too large. We know how to prove that. Yeah? So it's not only a belief. I mean, it is based on the fact that we don't see why the integers should be accumulated more in some classes modulo Q than in some other. So if they are well distributed, this is true. Okay, what else? After that, I want to show you some okay, some Sieve setting. I'm not going to do much of general Sieve. Usually, I'm going to tell you that what I do for the primes can be extended. But in the first lecture, I have to show you a bit what I mean by extended, what are the conditions. So what does it mean to sieve? To sieve, you know the Eratosthenes sieve. What you do, you take a list of integers and you remove some that are divisible by the first primes. Yeah? So sieving is taking a host sequence, an interval, but maybe the value of a polynomial, maybe any sequence, UN, that's your host sequence, and you want to get the prime index. Okay? So from this sequence, you want to extract some people. For instance, for the prime twins, you want to extract from the list of integers the ones that are prime, so that p plus 2 is a prime. Okay? So sieving is that. It's really from a set, deduce information on another one, okay? It's not like what we do when we use L functions. L functions, we use analytic property, we use functional equation, we use many other things. It's not the same thing. So what does it mean to sieve? So I'm going to sieve an interval. We need one host sequence. And in the large sieve, it's always an interval. Here, an interval. So that's the interval 1, n. Or m plus n, it's an interval. That's so what you get in the large sieve. When you want to sieve something else, you use Selberg sieve, you use other things. Here you use an interval. Or else you ask Fourier if he wants to sieve some other thing. And then you need to tell about the classes that you want to remove. For instance, for the primes, for each prime p less than some bound, q, some bound. For the primes, q is the square root of n. You remove one class modulo p. It turns out that when you remove things, it's algebraically not stable. It's better if you take the classes you keep. So for each prime, we keep, what do we keep? We keep the integers that are not divisible by prime. Okay? So 1 to p minus 1. So usually we say we remove 0. I say I keep 1 to p minus 1. The advantage is that I can say modulo q, I keep the invertible elements. Because the one you keep are stable by multiplicativity. The one you remove are not stable because of crossed. We keep a set which I'm going to call KP. That's capital K. It's a LaTeX matcal K. Okay. But if you see that in my note, it's a set inside Z by PZ. And I need to define KQ, which is by multiplicativity. Cativity. I'm going to, for each square free Q. So what does it mean that I define the set by multiplicativity? You know Q is P1, P2, Pk. Let's say P1, P2. K sub P1, P2, you take the Chinese remainder morphism from Z, from P1, P2 to Z, from P1 cross Z by P2. Here you have KP1 cross KP2. Take the reverse image, you get KP1, P2. It means that locally it's the same. That's what I mean by multiplicativity. If you want to do it for non-square free stuff, it can be done also, but I don't want to enter this kind of difficulty. So it takes a very long time to explain that, but it's trivial. You know? I mean, it's just vocabulary. You know? Don't get phased out by this stuff. It's just vocabulary. So for the primes, what is my set? Q equals square root n. Okay, I say it doesn't have any prime factor less than square root n. In fact, if it's, I should put strict to be sure. And my set Kp, where it's 1, P minus 1, and Kq, in fact, it's Z by QZ, invertible element of cardinality phi of Q. If you want, for the prime twin, that's more fun. Same. Q equals square root n. And then Kp, well, you should remove 0 because you want that P is a prime, but you want also that P plus 2 is a prime. So you have to remove minus 2. Because minus 2 plus 2 is 0, it couldn't be a prime. So it's 1, 2, and P minus 3, P minus 1. And of course, if P is too small, if P equal to 2, so that's for P larger than 3. If for P equal to 2, K2 is 1. There's no condition. Okay? You just remove 2 classes. If you want to know whether P plus 4, P plus 6 are primes. Okay, I'm sorry, I'm using P in 2 ways. In the sequence that I detect, it P, and also in the size here. So if you want to detect the sequence of integers so that n is prime, n plus 4 is prime, n plus 6 is prime, you remove 0, minus 4, minus 6. For each prime, you make the product. The cardinality here, it's P minus 2. Okay? So it's P minus 2. This 2 is what we call the Sieve dimension. Okay? For each prime, the Sieve dimension is a bit more complicated, but essentially it's the same. Okay. Cool. If you want to sieve the Gaussian integers, primitive Gaussian integers, it's the people who don't have any prime factor congruent to 3 modulo 4. So the sets that you define, if P is congruent to 3 modulo 4, you remove the class 0. Okay? If P is congruent to 1 modulo 4, you remove nothing. So Kp is everything. For the Leucian integers, if P is congruent to 2 modulo 3, you remove one class, 0. Otherwise, you don't remove any class. And I let you do my funny example number 4. Okay, that was one part. There was another thing I needed to do. I need the last 15 minutes for the infinite place, but I still have 5 minutes. So that's an easy one, because you'll find that very often. So G of Z is a sum for D less than Z of mu square D upon phi of D. It's a D, it's not a Q. Phi of D is larger than log Z. I've spent one part of my life evaluating this function explicitly with a main term, a constant, an error term explicitly. Okay. But essentially, it should be trivial if you don't look at explicit stuff. And to prove the inequality here, it's beautiful proof. So mu square 1 upon phi of P, it is equal to 1 upon P minus 1. Okay. It's equal to 1 upon P times 1 upon 1 minus 1 by P. It is equal to 1 by P plus 1 by P square plus 1 by P cube, and so on. Okay. Now if you have mu square Q, so a Q which is a square free. Okay, no, I need lots of space because I need to write many things. This one. Assume that Q is equal to P1, P2, PR, and it is a square free, so they are distinct. So 1 upon phi of Q, it is equal to the product of this one. Product upon I from 1 to R of 1 upon Pi plus 1 upon Pi square plus 1 upon Pi cube plus and so on is equal to what? I have to think a lot. The difficulty is not to understand what happens, is to know how to write it. The sum for L larger than 1 of 1 upon L when you do all this product. And what is it? It's the square free kernel of L divides Q. So K of L is a product for P divides L of P. So you need to think a bit to understand that this one is equal to that. Okay? There's no way I can write it. I mean, I can write more and more and more. It's not going to make you understand what it is. You have to look at that and see what happens when you multiply everything. You get any L, provided the prime factors of L appear here. And you get that with any power, and you get that only once. Okay? I thought a lot about how to write this proof. There's no way. You have to make the effort yourself to see that it is trivial. Okay, once you have that, you go to the other side. So G of Z, and yeah, I did a mistake, or no, it's okay, okay. So G of Z, in Sieve theory, you'll see many functions that are called G. like that. It always has to do with the density of the given sieve. For me, it's only going to be attached with the prime, so it's always going to be mu square of d upon phi of d. That's all. I forgot to prove something. Anyway. So d of z is a sum for d less than d of mu square d upon phi of d. And of course, I'm sorry, I changed notation between q and d. That's my life. So it's equal to the sum for, think of it, L larger than 1 for k of L less than z of 1 upon L. Because this one, mu square d upon phi of d, is the sum of 1 upon L for, oh no, sorry. The square free kernel equal. There's no one. It's equal, sorry. Otherwise, the proof here is false. That's good. So here, so 1 upon phi of d. Well, let me put q so that we recognize. It's the sum of 1 upon L for all the L so that the square free kernel is equal to q. And we can sum of all the square free kernel that are less than z. So it is this sum. And this sum is surely larger than the sum of 1 upon L for L less than z. Okay, you have the feeling that you're losing many things. In fact, we can show that g of z is equivalent to log z. So you see, and this one is larger than log z. So with that, you have a complete, what is missing from my proof of the Brundtland march is the last Sieve inequalities that I prove tomorrow. Just now, I've shown you some local estimate. So what happened with SA by Q, and also a bit of density. But essentially, that was what was happening in Z by QZ. Okay. If you've done some algebraic number theory, you'll know that you have to handle the local places modulo Q, but also modulo the infinite place. For that, I need a lemma that I'm going to state, and I'm not going to prove. And that's going to be the end of this lecture. Okay. So size condition. I'm going to tell you that there is a function which is an upper bound for the characteristic function of the interval and whose Fourier transform is compactly supported. So that's from Fourier analysis. But what you should read is a paper by Jeffrey Waller of 1985. This paper is written by a specialist of harmonic analysis and complex analysis, but it is beautifully written. You can read it, you'll learn lots of things. There's a pile of material in it. So we've been using this paper, all of us, for a very long time. We always refer to it, so you should know it. It's extremal functions in Fourier analysis. Something like that. I'm sorry. Let me check. Let me check. Yeah. Some extremal functions. And the Americans, they like, Jeffrey is American, so they like to put capital everywhere. I never know when I should put the capital and not the capital. Anyway, you'll find this paper, and really I recommend reading it, even if you're just having a look at this course. It's wonderfully written, and you'll learn things. I mean, it's elementary enough. Okay, so I want to state things explicitly. Okay. So I'm just going to give you definitions and theorem, and then some drawings. Berling in the 30s introduced a function. So look at the function h of, no, sorry. Yeah. So from this paper, I extracted many formulae. So this one is, of course, in one, when t equal to 0, it's one t times pi t times 1 minus integer part, absolute value of t plus cotangent times cotangent pi t plus t if 0 P1, it's 0 when t is larger than 1. The function, you'll see its interest later. That's how it looks. 1 minus 1, it is symmetrical. Don't believe my drawing, but essentially it has a sharp peak here. Oh no, sorry. Up. It's a very bad drawing. It's a very bad drawing. It's a decreasing function. I took some pain showing that it's decreasing. Non-negative and decreasing. Non-negative and decreasing. Okay, sharp function. And then I want, okay. Function h of z equals, no, sorry, it's too high. H of z, it's sine pi z upon pi z upon pi square times 2 upon z to the sum for m in z of sine m upon z minus m. No, where? That's an analytic function. And a simpler function, k of z, which is almost this one, sine pi z by pi z square. And what you have is b of z equal h of z plus k of z. This one is an analytic function that has been introduced by Berling in the 20s, that has been rediscovered by Selberg in the 50s. So this one is called the Berling-Selberg function. As you can see, it's an analytic function. On the real line, it's an upper bound of the sine function. So it's minus 1, jump in 0, and then 1. I mean, on top of 1. Okay? So you get something which is very badly behaved, which is a sine function, minus 1, 1. And you can bound it above with something which is extremely nicely behaved, which is this guy. So that's going to be the content of the main lemma, which is now. Yes. How do you want me to write it?
see.
Yeah. So you see it is made so that this one has a zero when this one has a pole. Yeah, it's so the theorem I need my sheet of paper. Delta positive and M positive also, in fact, larger or equal to 0. The function I define C of minus M and delta. Parameter, I guess, is U, yes? Ah, no, not U, X. That's going to be 1/2 of B of delta minus M minus X plus B of delta M minus X, should be? Yes. No. X minus M. C of minus M delta is an upper bound of the characteristic function of the interval function of minus M. Okay. And I can be extremely explicit, which is going to help us later. The Fourier transform of this person, the Fourier transform in analytic number theory is always the integral of the function between minus infinity to plus infinity of exponential 2i pi tu. We put the 2 pi. In PDE, you don't put the 2 pi, but we put the 2 pi. Sometimes it's minus, sometimes it's not minus. We never know exactly, but what is important is the 2 pi. So this Fourier transform, it's very simple. It is given by delta minus 1 minus u by delta. Okay. Could be cosine 2 pi m. Oh, I've put a t, sorry. If I put a t, I should put a t. mt, okay. Plus j hat, plus, yes, j hat of t by delta sine 2 pi m t upon pi t. You have to see that this one is only some, it's a very simple function. It is this guy, okay? It is long to write, but it's only some cotangent times some sine, I mean, it's a very trivial function. So the Fourier transform is a very trivial function. And this one is an upper bound for my function. It has an advantage. That's true. So when t is less than delta, and when t is larger than delta, this Fourier transform vanishes. That's a miracle. It vanishes. Usually, you say the Fourier transform of the characteristic function of an interval, it's something that has a sharp peak in 0 and then decreases fast. Okay. What we say here is that it has a sharp peak in 0 and it's 0 outside. So it will simplify our analysis a lot. The only price we have to pay is that we have to replace the characteristic function which was the precise stuff that we wanted to study, with an upper bound. Okay? But this upper bound is not too much, is not too large, because we have C of minus C hat of this one. So C hat at the point 0 is the total mass of my function. It is equal to 2m plus delta minus 1. Okay? So that's the mass of the characteristic function of minus mm. That's 2m. What you lose is delta minus 1, which is your parameter here. Okay? So now I'm going to do some drawings, and okay, it is recorded, but believe in my drawing still. So what you have is this minus m, okay? You have, yes, that, no, blue, you're not going to see much. You have your function here. That's the characteristic function you look at. No, it's too big, sorry. Up. I'm going to put m a bit closer. Okay. M is here. M is here. Okay. So what is your function doing? Your function is coming from infinity. It's an upper bound. It's slow. Then it sees that it has to jump. So it's getting some muscle. And it jumps. And it goes slow and symmetrical. Jump. Okay? And this part here, it's about delta minus 1. Okay? So you see that the mass is about the mass of this one, plus what you've added, which is about delta minus 1, maybe it's delta minus 1 by 2, something like that. But that tells you how you should select your parameter. If you took delta minus 1 too big, then these two bump, collide, and you get other things. Okay? Yes. Yes. You have to use something. It's essentially you have to take some energy to do the jump. I mean, you cannot do an approximation. I mean, people who don't do analysis may believe that you can do approximation, just do a drawing very close, and you do a little round, and then a little round, and it's going to work.
You approximate the discontinuous.
Yes. It's and I have to give you another drawing. This one is J. Oh, I have to. So this one is a C. So of course, I give you C minus MM because the expressions are better, and because the drawing is easier. But you can shift this interval. That's why I have this notation minus MM. Usually it's M plus N. But you get a better expression with one less parameter if you don't shift. And okay, the last one is this one, the C hat of minus MM delta. So in delta here, well, here, sorry. Minus delta. So this function, it has a sharp peak here, okay? But it is a slightly negative. Okay? It's not non-negative. There's a little bit that we lose. We really don't lose much, and the hump, the peak is very big, but you cannot use the fact that it is non-negative. So that's how we will handle the infinite place by using this upper bound. For proof of that, really the best paper is the one of Baller. If you want to see about the history of that, you can have a look at lectures on Sieve by Selberg, written in 91. It's inside the collected work of Selberg. There's a part where he described how he built this function and how he thought about it. So if you're interested in that part, and that's all. See you tomorrow. Huh? You have to define optimality, yes. Yeah, it is, but it's true, it's important. It's optimal in some way. So it's again a part where we won't be able to do better because, okay, thank you.